Yeah, welcome to the third session on countable and uncountable sets. Probably this will be the final session, at least on the topic on countable and uncountable sets. So yesterday we defined countable sets in the last session, and we also showed that R, any non-degenerate interval, is uncountable. Okay. So we also showed, because of that, the set of irrationals is uncountable. Okay, right. So you can see R is much bigger than the set of rationals, but set of rationals Q has the same coordinate as set of natural numbers. Okay, and now therefore irrationals is also as very big when compared with the rational number. That's the intuition we had, because it's uncountable. Okay, it's an infinite set but not countable set. That's what it means. Okay, now let's look at one more important result which many times people ask and try to understand, and it also has historical significance as usual. So let us start with complex numbers. Okay, I say a complex number alpha in C is an algebraic integer. Algebraic number. This is a definition. If there exists a polynomial with integer coefficients, so that polynomial, let us say P, so that P of alpha is 0. That is, alpha is a root of integer polynomial. In fact, you will see some books will say something like this: a n z power n plus a n minus 1 z power n minus 1 plus a naught, where all a k's are in Q. But you can just multiply by a GCD of all these fellows and then bring it to an integer coefficients. If you understand, it's well and good, otherwise ignore. So for us, an algebraic number is the root of a polynomial. What kind of a polynomial? It's a polynomial whose coefficients are integers. You see, these are internalized. Okay, just don't repeat the same definition. Try to say it in your own words. You may be right, you may be wrong, but try to say it. Slowly you will improve and you understand the definition in depth. That is what is called internalization process. So you should internalize. This I had been using many times. So those of you who had watched a lot of my videos will know this. Okay, whenever you see a definition, stop. Try to put it in your own words, try to understand in different way. Okay, right. So what we want to prove is the set of algebraic numbers in R see, it's a complex number, right? If in R is countable. In fact, it is also true in C, but I have not proved a fact about C. Okay, so I am not doing that, but it actually in C also. Okay, if you want, we will go through that proof also. That's not very difficult. Okay, in C, because the proof is the same. This is the result we want to prove. Notice that every rational number is an algebraic. If alpha belongs to this, then alpha is algebraic. That is very clear, because if x is p by q, then you simply write qx minus p equal to 0. This is a polynomial with integer coefficients. You see that? Therefore, my q, okay, see, look at that. Result is contained z. This is, and this is contained, let me call it a for algebraic numbers. Okay, so and for example, square root 2 is an algebraic number, because x squared minus 2 equal to 0. Right? So you can see that q is a proper subset of a. Right? And similarly, if I have something like nth root, if alpha is, let us say alpha is positive, and let us look at the nth root and is a natural number, then this is all algebraic, because x power n minus alpha equal to 0. And suppose alpha is, okay, let me take alpha is a natural number. Okay, alpha is a natural number and n could be anything. So and most of them you know are not going to be rational, most of them, because I can take alpha to be 2 cubed, therefore alpha to the power 1/3 will be 2 only. You understand? So are you following me? Try to think. Okay, is this clear? Okay, now how do I prove that? So let Pn be the set of nth degree polynomial, set of nth degree polynomials with integer coefficient. Z. Okay, therefore how will it look like? It will look like something like a0 plus a1 x plus an x power n with a not equal to 0, and all my ak's are in z, right? So if I give two polynomials p and q, when are they equal? If I write b1x nth degree polynomial, they are equal if and only if ak equal to bk for all k, right? Right. Therefore I have a bijection of Pn with z cross z cross z n plus 1 times. Because you give a polynomial of this kind P, I map it to the ordered pair a0 a1 an, ordered n tuple, n plus 1 tuple. Okay, so this is a bijection, right? Therefore okay, Pn is countable, because we know Z is countable, and if A and B are countable, A cross the Cartesian product A times B is countable. Therefore by induction, okay, Z cross Z cross Z n plus 1 times the finite number of times, that is countable. Is that clear to all? Okay. Now let's go to the next one. Now given any polynomial Pn, let R of P, okay, R be a set of roots or zeros. Simply says it will be P of alpha is 0, then I say alpha is a root in high school, and BSc in MSc you try to say it's a root 0 of, okay, that's the only difference. Okay, the set of zeros of P. Okay, and we know from algebra if P is of degree n, okay, this set, okay, will have the number of elements in Rp will be less than or equal to n, and if you allow complex roots, is actually equal to n. If you allow complex roots, and also we count with multiplicity, counted with multiplicity. For example, if I say something like x squared minus 2 whole square, that's my polynomial. Okay, this of degree 4, right? But square root 2 plus or minus square root is a root, but this is a 4th degree polynomial, therefore square root occurs multiplicity 2, minus square root also occurs with multiplicity 2, therefore it's 4. But actually it is, if I look at the set of roots, then it is actually 2 only. But that's why you say it's at most 2. Here also maybe I should say at most 2, because I am saying the set, right? The set, for example, for this polynomial R of P is only 2 elements plus or minus 2, therefore R of P is less than or equal to 2, equal to 2 less than or equal to 4. So it's better to write this way. Okay, with counted with multiplicity equal to n. Anyway, is that clear? Right? Therefore now let us look at the roots of polynomial and P in Pn. Okay, this P is, are you following? Let me write Rp, P is in Pn. Okay, for a fixed n, then this is a finite set. Okay, and what this Pn is a countable, this is a countable indexing set, the indexing set is countable, therefore countable, you know, countable sets is countable, therefore this is countable. Okay, pause, review, proceed. right? Now I can allow n to vary, n from natural numbers first degree to infinity. This is Pn of Rp. Okay, so this is what this set is: set of all roots of polynomials of degree equal to n. All roots, okay, whatever polynomial you give. Now I want to allow the degree also to vary, therefore I have this. Now this is already countable. Okay, call this as, if you want, an, right? Therefore union n in n of an, these are all countable, and this indexing set is countable, therefore countable we know, countable set, therefore this is countable. Okay, therefore what have we shown? We have shown the set of algebraic numbers is countable. Okay, pause, review, proceed. Yeah, sharing. Okay, right? Now let us look at this is a set of algebraic numbers, set A of algebraic numbers. Then let AR denote A intersection AR, A intersection R. That is, so okay, real algebraic numbers. For example, x squared plus 1, x equal to plus or minus I. This is an algebraic number. Yes, I belong to plus or minus I belong to A, but that does not belong to AR. Do you understand the difference? I am taking only those complex numbers which are actually real, but which also is a root of an nth degree root of a polynomial with integer coefficients. Is that clear? Try to understand what is AR. This is again internalization process, right? Therefore AR, see, AR is a subset of A, and therefore AR is countable. Okay, countable subset of R. Right? Now I say a real number A in R is transcendental if A is not algebraic. It is same as saying A is not in AR. Is that quite clear? For example, most of you, your teacher might already told you, look at E or look at pi, our two important numbers in real analysis. These are transcendental. This is C. What does that mean? There exists no polynomial with integer coefficient. That is, given any polynomial p with integer coefficient, p of p is not equal to 0 and p of pi is not equal to 0 with a non-zero polynomial, of course. You understand? Now R, I am writing it as AR union T, where T is R minus AR, right? What is T? T is a set of transcendental numbers. A real number is transcendental if it is not algebraic. Therefore, this is a disjoint union. That is, these two are complement to each other. Now I know this is uncountable, and I know this is countable. Therefore, conclusion is T is uncountable. Okay, and also it is a very large big set, because this is countable, this is uncountable, therefore this is uncountable, right? Therefore this will be much bigger. one should learn to appreciate this result. Okay, what does this result tries to say? Something very interesting. You ask any mathematics professor, teacher, student, PhD students, okay, have you read a proof of E is transcendental or a proof of pi is transcendental? These are the two important numbers in real analysis, right? You will be surprised. In all probability, I would say 99%, but let us say 90% of the mathematics teachers and students all put together in that universe. Okay, if I put the entire universe, that is student of mathematics, master's degree, PhD students who got doctorate, postdoctoral fellows, teachers of mathematics in various colleges and universities and institutes and research institutes. Okay, in that universe, if you take it, 99% of the people would not have seen a proof of E is transcendental, pi is transcendental, because they are non-trivial proof. Okay, so two numbers which all of us are familiar with, we are using, even to prove they are transcendental is very difficult. Okay, by the time Cantor came, only there had been sporadic results about which numbers are transcendental. Given a real number, when it is transcendental, there are only very few results, nothing more. Whereas Cantor comes and says, the set of transcendental number is much bigger than an algebraic number. That means you give me any kind of real number, it's very likely to be transcendental than thing. I just want to give you intuition. Don't get carried away. This is what I'm saying is true in terms of measure theory or in terms of something. Okay, you can do. In this case, it's only in terms of cardinality. Okay. Do you remember yesterday we said the set of irrationals is uncountable, right? That means it's an infinite set. It's uncountable. Therefore, the first infinity is, as you know, if it is not finite, then countable infinity. That is n natural numbers is the first infinity intuitively. Okay. Then next. Okay. Then this is much bigger than that. The set of irrationals. The set of rationals, the set of irrationals, the set of real numbers, they are all much bigger. They are all uncountable. So we are also saying the transcendental numbers are uncountable. That's something, it was shocking. Alright, you have to take a number and to try to show it's transcendental, so difficult, whereas this guy comes and says, okay, there are a lot of transcendental numbers. Okay, it almost saying that, okay, let me not say, anyway. Right, you follow that? That is why I said when Cantor proposed all this kind of thing, it actually shook the mathematicians. You should appreciate that. Okay, we are going to do one more thing. Let's go back. Now let's look at the set of functions from natural numbers to 0, 1. All functions. This is my set. Okay, I say this set is uncountable. This is a very often used fact. In fact, I can simply say it follows from earlier result, but let me just give you direct proof. Okay, suppose it's countable. Suppose F is Fn and n where, that is, assume it's countable. Assume F is countable. Let phi be a bijection of right, and phi of Fn I denote by Fn. Therefore my F as a set is Fn as n varies over capital N. Right. Again we are going to use Cantor's diagonal trick. So define a G from natural numbers to 0, 1 so that G of n is not equal to Fn at n. Right? If, what do you understand? That is, G of 1 should not be equal to F1. If F1 is 0, then take this to be 1. If this is 1, take G of 1 to be 0. You understand that? There are only two choices. You have to define the other one. Right? So G of n equal to 0 if f of n is 1, equal to 1 if f of n is 0. You understand this? Alright, so each f you can take, right, think of it again as we did earlier. Yeah, maybe I will do that. Suppose f1 is going to be f1 at 1, right, f1 at 1, f1 at 2, f1 at n, and so on. Fn will be fn at 1, fn at 2, fn at n. What I am going to do, I define as g said that g of 1 is not this, g of 2 is not this, g of n is not this. Since g has to take values between 0 and 1, you just avoid that and take the next element. So it's a well defined function now. Do you understand that? Now therefore g is a function from n to 0, 1, but g is not equal to fn for any n. Why? Because g of n and fn at n, they are distinct. Therefore this is not equal to. Okay. Therefore f is not countable. Is uncountable. Pause, review, proceed. So this result can be used to prove, for example, 0, 1 is uncountable. But it requires binary expansion. Okay, I don't want to that is any number x here, you know, it can be written as 0, x1, x2, xn, where my xk lies in between 0 and 1. All of you now would have learned computer programming, so you would have learned this binary representation. Okay, that thing. Okay. Because any x, therefore I have, you give me an x, then it corresponds to a function f in script f, which is set of all functions f from n to 0, 1. Namely, you define f at n to be xn. Given x, therefore my x, you understand this? X, if you think of as x1, x2, xn, etc., and f equal to f of 1, etc., f of n, that's all. I simply map x to f whose value f at 1 is x1, whose value at n is xn, that's it. So this is a bijection. Therefore I know this is uncountable, therefore this is uncountable. Okay, this is a little fast, but I don't want to spend more time on that. Please go through it. Let me see, I am sharing. Yes. Okay, now there may be a few more things which I might have forgotten, but I have given enough background so you can read from our book on foundation course, Ajit Kumar Kumaris Baba Sharma, or you can read from Monkr's topology. It also has a very nice way of writing, so you can look at any one of the two books. There is one thing which I want to say. See, before Cantor, everybody thought infinity, there is only one infinity, whatever it may mean, or only one kind of infinity, if you want to say. And do not try to understand this very rigorously, because at the time even people are not careful about what is infinity. They thought, okay, for R of course we say minus infinity and plus infinity kind of thing. When I say infinity, okay, it's not that number, I am talking about infinite sets. Let me say there is only one kind of infinity among sets. What does it mean? See, if I say n is also infinite, R also infinite, they did not know they are different kinds of infinite sets. Am I making myself clear? You take n and take R, we had already done. Okay, both are infinite set, but while this is countable, this is not countable. Alright, so even though they are infinite, there seems to be some difference. That's what I meant. Before Cantor, people didn't even realize, possibly. Okay, I am not good at history. Okay, and somebody should not jump at me. Okay, it may happen. Okay, what he proved was not only this, he said a countable number of different infinities he can show. That is, Cantor said or exhibited a countable sequence of different infinite sets. Okay, I will prove that. What here is, start with X an infinite set, for example n. Okay, then let's look at the power set of n. Okay, and then that is contained in power, not power set, sorry, not n. Okay, then look at p of x, then p of x. Now by induction pn of x, that means power set of the earlier one, pn minus 1 of x. Okay, these are all sets, right? This is, you know, this is countable. I have to show this is uncountable. Okay, I will show that in a minute. Okay, I will show it's uncountable. Okay, now I will say none of these things are equal. What do they mean? Okay, let us try to understand. I have two sets A and B. Okay, I say this is the notation, cardinality of A is less than or equal to cardinality of B. I read it as cardinality is less than or equal to cardinality of B if there exists a 1-1 map f of A into B. So intuitively, what does it mean? It says B has at least as many number of elements as A. Keep the intuition also. Okay, even the intuition, okay, may give us some wrong thing, but it's good to have. That why we are saying this, right? Now there is a theorem due to Schroeder-Bernstein, which you can find in my book. Sometime I will give us a video on that. It says if there is a bijection from A injection 1-1 map and another injection from B to A, then there is a bijection H from A to B. That is, you see that now it's anti-symmetry. If I give two real numbers x and y, if I say x is less than or equal to y, y is less than or equal to x, okay, then using law of trichotomy, I say x equal to y. Similarly, it says that among cardinal numbers also, it's a true statement. That is, I have a set A, so that cardinality A is less than or equal to B. I also know cardinality B is less than or equal to A. Then their cardinalities are the same. When do they have the same cardinality according to our definition? If there is a bijection f from A to B. Schroeder-Bernstein theorem says. It's a very nice proof. Sometime we will see later. Okay, you can also read it from my book. Okay, read it from our book. Okay, or later we'll see a video. Right? And there is a theorem by Cantor. This I will prove it now. Suppose x is a set. Look at a power set of x. Okay, there is a natural 1-1 map. Do you see that? I can have a natural 1-1 map. Give x. What is the natural? I want a subset of x. Give me an x. What is the natural subset of x I can think of? Singleton x. Okay, this is a 1-1 map. Okay, but is here x has, okay, if suppose x is finite, let us say x has number of elements, then all of you know p of x has 2 power n elements. So even n equal to 1 or even n equal to 0 empty set, this has 1 element. You understand that? So we know this map is never onto, at least in the finite case. But what Cantor proves is, let x be any set, okay, then there exists no onto map. Here from x to p of x. Okay, that means, are you following this? Try to understand what this is. If suppose x and p of x have the same cardinality, then there should be a bijection, right? X to p of x, there should be a bijection, right? That means this bijection will naturally be onto. You understand? I already know x. Okay, this is less than or equal to p of x because there is a 1-1 map. Go back to this. If there is a 1-1 map of a into b, then I say Cardinality of A is less than or equal to cardinality of B. Therefore, I know from here cardinality of X is less than or equal to cardinality of Bx. Okay. Are they equal is a question. Okay. If they are equal, that means there is a bijection. If there is a bijection, then there is a map from X onto P of X. Cantor's theorem says no such thing exists. Right? Therefore, in such cases, what will I write? If I say A is less than or equal to B, but A is not equal to B, then I will write A is strictly less than B. Therefore, I will say cardinality of X is strictly less than cardinality of Px. Okay. So, second thing. Now come back. Okay. I will give a proof in a minute. Now go back to the thing. Suppose I have n, P of n, and P of n, which is P squared of n, and P power K of n. Okay. Then cardinality of this is strictly less than cardinality of this. That is strictly less than cardinality of this, and that is strictly less than cardinality of this. You understand that? So this is infinite. Therefore, this is also infinite. Everything is infinite. But I have given a sequence of sets whose cardinalities are bigger than the earlier one. Okay. Please appreciate this. So we will prove Cantor's theorem. If X is empty, if suppose X is empty, then power set of X consists of only singleton element. Alright, therefore there is no onto. Okay, so let us assume X is non-empty. Right. Okay, suppose false, proof. Okay, again as usual, proof by contradiction. This is a mind-blowing proof. When I was in let me just make eye contact with you. See, I learned set theory only in the first year of MSc in my days. Okay, all of you would have learned 7th, 8th or 9th standard, right? I learned only when I was first MSc. In fact, all my generation, okay, all people of my generation learned only at first year MSc. We learned something about set theory. And this Cantor's theorem, when I read, I couldn't sleep. I was so excited by the argument. Okay. It was fantastic. Now I can really see how mathematicians of his time, contemporary mathematicians, would have been really vexed, confused, and excited, a mix of everything, astonished, stunned with the results of Cantor. I hope I am able to convey at least part of that to you. Okay, suppose there exists f from x to px which is onto. Okay, now I want to arrive at a contradiction, right? So if you give me an element x in x, okay, fx is in px. What does it mean? Fx is actually a subset of x. You understand? Now think of a set x and think of a subset. Okay, yes, and you give me some element x in s. What is the natural question you will ask? I have an element x in x, I do not know where it is, and you are given me a subset s. What is the next natural question you will ask? Right? Suppose you are a student of a college, okay, and this is all, let's say, I mean, for second year or final year BSc students, okay, final year students BSc, right? You meet a student X, then what you will ask? You would like to know whether he is in your class or he is not in your class. You understand? So natural question is whether X is in yes or X is in not in yes. This is the question we will ask. Right? Now try to understand this. So you have told me for each x in x, okay, fx is a subset. Therefore the question is, does x belong to fx? You understand that, right? So I have x, okay, this is all subsets x. These are all the subsets. So you give me x and this is my fx, okay, then I want to know whether x is going to be in fx or not, right? So let us define the set S to be set of all x in capital X such that x is not an element of fx. Notice that S, now S is a subset of x, that is S is an element of px. It may very well be empty, I don't care, yeah, but S is a subset, okay, it could be empty. You understand that? So the question I want to ask is, okay, since yes, f is onto f from x to, let me use this thing, f from x to px is onto and s is an element, then I want to, there exists an x in capital X such that fx is x equal to s. Do you understand this? Because it's onto and this is an element of this, therefore there is x, right? So there is an x such that fx equal to s. Now what is the natural question again? We will ask, does x belong to fx, which is yes. Please think, pause, review, proceed. Okay, I constituted, I kind of formed a set S. What is the set? It is set of all elements in X so that X is not element of its image. Very good. It could be empty, it could be non-empty, I don't care. But that is a subset of X. But F is onto, that means there is an X so that Fx is S. Therefore, what is the natural question I can ask? I can ask whether X is in Fx, whether X is in S. Right? Now you will see you are going to get kicked both ways. Okay. So what are the possibilities? Case 1 is x is in fx, and case 2, let me write a different color scheme. Case 2, x is not in fx. Right? Now let us use, suppose x is in f, okay, that is your s, right? But fx is yes. But if x is, but that means therefore x is in s. X is in s, look at the definition, when x is in x, if only if x is not in fx. So this implies x is not in fx. So look at this, a contradiction. So go through slowly, okay, for this alone PRP. Start with x, suppose x has to be in fx, but fx is s, right? Since x belongs to s, what is the defining condition for s? X should not be an element of fx. So I got x is not in fx. So these two things are contradicting to each other. Contradiction, right? Contradiction. Right? Now let's look at that. Suppose x is not in fx. Okay? But this is okay. But fx is yes. Therefore that is x is not in s. Right? But if x is not in fx, look at the definition of x is not in fx, that means x must be in s. That means x must be in fx. But fx is yes. So you start with x is not in this and you arrived at x in fx. Again, let me repeat. Okay, so as I said, mind-boggling. For the first time if you are learning this. So suppose x is not in fx. Okay, now let us look at the definition of s. If x is not in fx, what does that mean? It must be an element of s. Therefore x is an element of s. Right? If, right? So sorry, x is not an element of s. So, I'm sorry, x is not in fx. Okay, that means okay, x has to be an element of s, right? If x is an element of fx, that's a contradiction. Yeah, am I confusing? Let's start. Suppose x is not in fx, right? If x is not in fx, by the definition of s, yes, x is in s, but s is fx, therefore x is in fx, a contradiction. So given x and this is subset, exactly one and only one of them must be true. Law of dichotomy, right? Either x is in fx or x is not in fx. Whatever way I assume, I arrive at a contradiction. So what does that mean? My assumption that there is an onto function from f from x to px is false. Okay, go through the proof. So go through the proof, enjoy. Okay, in fact after that you should be close the thing, video, try to see. If x is in fx, that means x is in s, but if x has to be in x, the condition is x is not in fx, a contradiction. Suppose on the other hand x is not in fx, but that is the defined condition, therefore x has to be in s, but s is fx, therefore x is in fx. Okay, it looks really simple after once you get it. Okay, but if you are a beginner you may get stuck. Okay, I'll just end my lecture with a personal experience. One of my colleagues was trying to explain this proof to students. Okay, and he didn't succeed. Then he asked me, well, Kumarisan, can you try to explain this proof to them? I just prepare my students with the following real life episode from my life. Okay, there is a cave, there is a stalagmite, you know that. Okay, there are, right? So the belief is you toss a coin, if it sticks to the roof, you make a wish and toss a coin. If the coin sticks to the roof, then your wish will be granted. Okay, my tourist guide told me, he was actually a famous mathematician. Then I said, okay, my wish is my coin should not stick to the roof. Think about it. I hope you enjoy. Right? Let me stop.